everyone. Uh, Today I'm going to be walking you through a type of easy bridge known as the Owens Bridge. Easy bridges are basically in instrumentations a method of measurement of unknown impedances such as inductance, resistance, or capacitance. And Owens Bridge is one of those easy bridges, but Owens Bridge measures unknown inductance in terms of capacitance in a circuit. So it's a way for us to measure unknown inductance of any component. So I'm going to be using a PowerPoint presentation to walk you through everything you need to know about Owens Bridge. So starting off with the basic introduction, Owens Bridge is an AC bridge used for measuring unknown inductance in terms of capacitance. The way it works is it works on the principle of comparison, where we compare that unknown inductance with the standard capacitance. This will all make much more sense once we take a look at the circuit. So now we're going to look at the circuit. So this is the circuit diagram for Owens Bridge circuit. Here we can see different components used, but it's basically an RLC circuit. So an Owens Bridge has 4 arms, one going from A to B, B to C, C to D, and D to A. And our unknown impedances will be at arm AB, which is R1 and L1, and we'll have known resistance R3, known capacitance C4, and variable resistor and variable capacitance R2 and C2. And E here is the voltage drop. E2 is the voltage drop of arm AD. TC's voltage drop is E4, E3 for BC, and E1 for EP. And this is the total voltage drop across the entire circuit, which is being supplied through an AC source. Now, we know that this is the circuit, but how do we actually measure unknown inductance? That is done. We're going to keep our circuit on the side, and we're going to derive some expressions through which we can actually measure the unknown impedance. So for an Owens AC bridge, we have something called the balance equation. That is when our detector here is at null position, meaning that there is no current flowing through this, meaning that the voltage drop E1 is equal to voltage drop over here, E3. So when E1 equals E3 or E2 equals E4, or when the detector is at null position, we obtain an expression that the impedance Z1 and Z4 is equal to Z2 and Z3. Now identifying each impedance, Z1 is the impedance R1 plus J omega L1, which is the inductance. So it is the impedance at arm AB. Z2 is the impedance across arm AD, where we have R2 plus 1 divided by J omega C. And Z3 is just R3. Z4 is 1 divided by J omega C4. So on substituting all the known impedance values into the equation, we get this. And when we perform some basic algebra over here, we get this expression. Here we can see that there are some real terms and some imaginary terms. Real terms being those without J omega, and imaginary being those with J omega. So on comparing imaginary and real terms, we are getting L1 divided by C4 equal to R2 R3, and R1 divided by C4 equal to R3 divided by C2. So from here we can play around with the quantities, and we finally get the expression L1 equal to R2 R3 and R1 equal to R3 C4 divided by C2. So because we know the values of R3, C4, R2 and C2, we can now find the unknown impedance R1 and L1, which will be equal to Z1. Their sum will be Z1, so that is how we are able to find the unknown values. Now here is the phasor diagram for the Owens Bridge. The phasor diagram The reference phasor we are taking is current I1, which can be, if you look back here, I1 is the current which is from this source, AC source. I'm taking I1 as phase. Now following the flow of current through arm AB, we have first the I1 flowing through the resistor R1. So when the current flows through a resistor, it will be in phase, the voltage drop will be in phase to I1. And then when the current flows through the inductor, I1 X1, then we're gonna have a voltage leading the current by 90 degrees. We have voltage leading the current by 90 degrees, and it is out of phase with I1. So these two vectors are the voltage drops across arm AB. So the sum of these two vectors should be equal to E1. So that's what we're getting over here. The sum of these two vectors is E1. And now moving forward to the arm B, A and arm AD, we are taking I2 to be the reference current or reference phasor, and when the current flows through resistor R2, it is in phase, but when the current flows to the capacitor, the current voltage lags current by 90 degrees. So here we have this, and then when current, so now plotting for the other arms, E3 is just I3 R3, and now we're assuming that the inductor is balanced meaning E1 is equal to E2 and E3 is equal to E4. So that's what we're getting here. So we can use this to plot it on the same line. So when it flows to the resistor, it is in phase with I1, which is its reference phasor, and when it flows to the capacitor, it is out of phase, 90 degree lags with the reference phasor I2. So that is the phasor diagram for an Owens circuit bridge. This was video 1, where we are looking at basic operations, basic construction, operation, and the phasor diagram of an Owens bridge. In the next video, we'll look at some applications, advantages, disadvantages, and some numericals using the formulas we derived. Thank you.